All right, so I'm gonna look at the syllabus really quickly. I know that we're supposed to talk about complex numbers today, but I want to see whether or not I intended to do a review of sinusoids today or not as well. Or if that was going to be our next class meeting. This says complex numbers. We might touch on sinusoids. All right. So review of complex numbers. So a complex number is any number that contains both real and imaginary parts. So what I'm going to do here is I'm going to put a plot here in the middle of the page. And this is going to represent an imaginary, or excuse me, a complex plane. So the horizontal axis corresponds to real numbers, where to the right means positive real numbers and to the left means negative real numbers. And then our vertical axis will correspond to imaginary numbers, where up is positive imaginary numbers and down is negative imaginary numbers. So there are multiple different forms that complex numbers can be represented with. The first of which is called the rectangular form. So in a rectangular form complex number, complex number A, and I'm going to denote that it is a complex number by putting a bar over it. And I could have that this will be lowercase a plus j b. So the real part of our complex number capital A is A. So I'm just going to write this down here. So the real part of A is A, and the imaginary part, complex number A, is B. So if we wanted to plot this complex number, we would go out A units in the real direction. So that's just arbitrarily going to be this number. And then we'd go up B units in the imaginary direction. And we'd wind up with this complex number, A. So we went out positive A in the real direction and up positive B in the imaginary direction to get this particular complex number, okay? So that's our rectangular form. Well, it should be fairly obvious to see that we could represent this complex number in a polar form by recognizing that this complex number makes an angle with the positive real axis. So I'm going to call this angle theta A. So using these polar coordinates, we can actually come up with two different representations. We'll have the exponential form, which I'll put here, and then I'm going to put the polar form over to the right. The exponential form and the polar form are literally the exact same information. They're just presented in a slightly different way, okay? So our exponential representation of complex number A would be the magnitude of A, so that's the length of it, e to the j theta A, and the magnitude of A angle operator theta A. So the magnitudes are the same, the phase angles are the same. The only thing that's different is this little e to the j thing. The polar form representation is just a shorthand notation for the exponential form. They are literally the exact same thing. Now, I want to be clear about something here. We might be working with exponential form complex numbers in this class. When you put them into your calculator, you absolutely have to use the polar form because your calculators cannot handle the exponential form, but they can use the polar form, okay? So in any calculator calculations that we do, always, always, always use the polar form. You cannot use the exponential. Okay. So let me just clarify something really quickly here. The magnitude of A is simply the length of this vector, okay? So we can use simple trig identities and relationships that we've learned in significantly lower level math classes in order to figure out how the rectangular form and the exponential and polar forms are related to each other, okay? So let's first work on how we might go about converting a rectangular form complex number into an exponential form complex number. So the first thing that we're going to need to do is figure out how the magnitude is related to our real and imaginary parts A and B. We have a right triangle here, which means we can just use Pythagorean's theorem. So the magnitude A is going to be the square root of the real part of A squared plus the imaginary part of A squared, which is nothing more than the square root of A squared plus B squared, right? So our magnitude is the hypotenuse of this right triangle. So we're just using good old Pythagorean's theorem that we probably learned in grade school in order to get this. Our angle theta A can be determined in multiple different ways, but the way that I prefer is to use the inverse tangent. So we would have arctangent of the imaginary part over the real part. Which is the same as the inverse tangent of B over A. This new stylus is writing properly. So that's how we can express our exponential and polar forms in terms of our rectangular. Now let's talk about how to go the other way around, right? So if I have a polar form complex number and I want to express it in rectangular form, well, the real part of A is simply the magnitude of A cosine theta A, and the imaginary part of A is the magnitude of A sine theta A. So that's how we can get from polar or exponential form to rectangular form. Okay. So there is a little bit of a hiccup when doing these conversions by hand. So if any of you guys are actually listening and paying attention, that would be great if you could get your calculator out. So what I want us to do is to convert the following complex number Let's say that complex number X is -6 plus J2 into polar form, right? So the magnitude of X is just going to be the square root of -6 squared plus 2 squared. So let's see, 36 plus 4 is 40. So that's going to be 4 square, 4 times 10. So 2 square root of 10 in magnitude, if my mental math is correct there. And then the angle theta x is going to be the inverse tangent of 2 over -6. Can't do that in my head. I get -18.435 degrees. See what's going on in chat. Driving but listening. Okay. So anybody else see a problem with the results here, particularly the angle?
It's negative.
Why is that a problem?
Wouldn't we have to shift it? Or I guess rewrite it maybe?
So the problem, you're getting there. The problem isn't necessarily that it's negative. The problem is that -18.435 degrees lies in quadrant 4. But based on our rectangular representation, it should our number should lie in quadrant 2, right? So let me draw this out, kind of explain things here. So if I go -6 out and then 2 up, that line isn't straight enough for me. This is where my complex number X should lie. And we can see by inspection that it should have an angle a little less than 180 degrees. Well, based on the inverse tangent relationship that we just used, we effectively got X down here. So the issue is that the inverse tangent operation on your calculator literally cannot tell the difference between the inverse tangent of -2 over +6 and +2 over -6. In fact, the inverse tangent operation will always give you a result that is in the first quadrant, or so the upper right-hand corner, or the fourth quadrant, the lower right-hand corner. It will never give you a result with an angle that would be in quadrant 2 or quadrant 3. So to fix this, we could simply add 180 degrees to force our result to be in the correct quadrant, which would look like 161.565 degrees, which makes a whole heck of a lot more sense based on our rectangular plot. Now, if you have taken my suggestion and you have purchased either a TI-36X, a Casio 115, or a Casio 991, you can use those calculators to convert from rectangular to polar and vice versa, and never actually run into this issue, which is one of the reasons why I suggest you guys use one of those good calculators, in addition to its ability to solve system of equations, okay? So I'm gonna experiment with something here. Give me just a second. What I'm gonna try to do here is use the rear camera and see if you guys can see me type stuff into my calculators. And I'm gonna use the 3 different calculators that I had mentioned in order to show you kind of how to do things. So let's see if I can get this going. The rear camera is on, so you get a glorious picture of a chair in my office. This is the TI 36X. So sorry, our complex number is -6. Oh, it's mirroring it. Plus 2i. Let me see if I can fix that as well. Should have tested this beforehand. Okay, now it's no longer mirroring things. Hopefully you can see this. So -6 plus 2i. And if I press second and then complex, and then scroll down here to option number 4, this is going to give me that result in polar form. And I get 6.324 and change, which I believe is 2 square root of 10 with an angle of 161.565 degrees. So it did the conversion correctly because this calculator is capable of doing that particular conversion. But it only works if I tell it to convert it into a polar form complex number. If I do it step by step, like we did in the practice problem, it will not work, okay? So for you TI using folks, effectively all of your complex number stuff is buried in this key, the pi EI key. If you hit second and then that key, you have your complex menu where you get your angle operator. Number 2 returns the angle of a complex number. Number 3 gives you the magnitude of a complex number. Number 4 converts a rectangular form complex number into a polar form complex number. Number 5 converts a polar form complex number into a rectangular form complex number. Number 6 performs the complex conjugate operation that we're going to talk about in just a couple of moments. Number 7 returns the real part of a complex number. Number 8 returns the imaginary part of a complex number. And then those are all of our options. So for the TIs, everything is buried behind this single key right here. All right, so now I'm going to get out my my Casio 115. So here's my Casio 115. In order to do any complex math, I need to press the mode button and press number 2 to put it into complex mode. Without putting it into complex mode, I'm not going to have access to the imaginary operator or the angle operator. So I want -6 plus 2. And to get the imaginary operator, I press the engineering button. Okay. My complex menu for this particular calculator is accessed by pressing Shift 2. So option 1 returns the argument, that's the angle. Option 2 performs the conjugate operation. Option 3 converts rectangular into polar, and option 4 converts polar into rectangular. So we're going to use option 3 here. Press equal, and I get 2 squared to 10, 2.819, blah, 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 which means my calculator is in radian mode. So let me fix that really quickly. Wait, degree. There we go. So 2 squared of 10, angle 161.565 degrees. Okay, so for those of you using a Casio 115, put your calculator in complex mode by pressing the mode key and number 2. And then all of your complex operations are buried in the engineering key. Well, actually, that's not true. Your imaginary operator, I, is gotten by pressing the engineering key. The angle operator for polar form numbers is shift negative. And then all of your manipulation stuff is gotten by pressing shift 2. Now for the Casio 991. So I'm starting out with it in the standard computation mode. For this Casio, I also have to change it into complex mode. So that is just, again, option 2 or tabbing over to the right one thing and pressing OK. I'm going to press 2. So now my calculator is in complex mode. So -6 plus 2 engineering button. And for this calculator, all of my complex numbers or manipulation is found by pressing the option button up here at the top left. So option 1 is the argument or the angle. Option 2 is the conjugate operation. 3 returns the real part. 4 returns the imaginary part. Scroll down to the next screen. Option 1 converts to polar form. Option 2 converts to rectangular form. And then I can change my hyperbolic function, engineering symbol, and angle unit. I've never used any of those operations, so I'm going to go back up and press option number 1. Press equal. And once again, I get 2 square root of 10, angle 161.565, just like we did with the other things. Okay. So this is how we basically input in things and can convert from rectangular to polar. And I believe I've shown you enough to be able to convert, input a number from polar form and then convert it back to rectangular as well, which means that roughly 2/3 of your in-class assignment is effectively done now. All I'm expecting you to do on this particular in-class assignment is learn to use your calculator. So if you have any questions about things about how to use your calculator, please ask or shoot me an email or anything like that, and I will tell you there's a reason why I have one of all of these. If you are one of the few people, and I've literally only had 2 students my entire time teaching this class that uses an HP calculator, I don't own one of those, so probably YouTube and Google will be your best bet. All right, so let me go back to the lecture for real. Okay. So let's talk about the complex conjugate operation. So this is the only operation that we're going to be dealing with that is specific to complex numbers. Okay. So if I have a complex number on the complex plane, like so, once again, we're just let's identify this as real, and this is imaginary. I'm just going to have some complex number here. Let's call this A. The conjugate of A is simply the reflection of this number across the horizontal axis. So A conjugate would be somewhere down here. We denote the conjugate by an asterisk symbol. Okay. So if you see any complex number and then an asterisk, that is telling you to conjugate that complex number. Okay. So in rectangular form, if A is equal to A plus JB, then A conjugate is simply A minus JB. So the conjugate operation on rectangular numbers simply changes the sign on the imaginary part. If instead we have a polar form complex number, and I'm going to do polar and exponential here. The conjugate operation changes the sign on the angle. So A conjugate would be the magnitude of A, e to the negative j theta A, or the magnitude of A angle negative theta A. This conjugate operation is something that we're going to have to utilize a whole heck of a lot later on in this class when we start dealing with the complex power relationships. That being said, if for whatever reason you can't remember it, your calculator can do it. For the TIs, press Shift 2 and scroll down until it says conjugate. For the Casio 115, Shift 2, excuse me, for the TIs, it's second and then the pi button. For the TI 115, it's Shift 2, and for the Casio 991, it's in the options menu. So press the option button. Right. So that's the conjugate operation. Simply flipping that complex number across the horizontal axis. So now let's talk about more common operations. The first one will be simple addition. So let's say that I have a complex number A is equal to A plus JB, and a complex number B is equal to C plus JD. If I want to add these two complex numbers together, that would look like A plus JB plus C plus JD. And this is just like adding vectors together in your physics classes, okay? So the real parts are going to add together. So we're going to have a real part. My stylus will write of A plus C plus J, and then an imaginary part of B plus D. So addition, fairly simple and straightforward. Addition by hand definitely works best in rectangular form. In fact, there's not a simple way to do it in polar form or exponential form. You would just convert back into rectangular form and then add the results together and then convert that result back into polar form. Okay. So addition should be carried out if you're going to do it by hand using rectangular form numbers. Subtraction is just addition, but now there's a negative sign involved. So if we have those same complex numbers, A is equal to A plus JB, and B is equal to C plus JD. If we take A minus B, we'll have A plus JB minus C plus JD. And so that's going to look like A minus C plus J, B minus D. So we're just taking the difference of the real part and the difference of the imaginary part. Okay. Subtraction, much like addition, is best done using rectangular form complex numbers if you're doing it by hand. I'm making that caveat there because your calculator literally doesn't care. You can add, subtract, do whatever. in either polar or rectangular form, and your calculator can figure it out. All right, so now let's do multiplication. And we are going to start by looking at things in rectangular form. So once again, A will be equal to A plus JB. And B will be equal to C plus JD. If I multiply two complex numbers by each other, I'm just going to put those two numbers beside each other, okay? I'm not going to use a dot to indicate multiplication because I don't want you to get it confused with a dot product, which is a vector operation. And these complex numbers are effectively two-dimensional vectors, okay? So the dot product is not used for complex numbers. I'm not going to use an X because that could confuse people with a cross product. Again, a vector operation that cannot be used for complex numbers. And I'm not going to use a star because we're using that for the conjugate operation. So literally, you will just have one complex number next to another complex number, means multiply them. So I'll have A plus JB times C plus JD. And now I'm just going to FOIL this out. So I'm going to have A times C plus J, A times D plus J, B times C plus J squared, B times D. Okay. So let's talk about J squared here. Okay. I didn't mention this at the beginning of the class, but J is literally the exact same thing as I is the square root of -1. We use J in electrical engineering because I is for current. Okay. So J squared is then simply the square root of -1 quantity squared or -1. So that means that I will have a real part that is AC minus BD, and then I'll have an imaginary part that is AD plus BC. So this is what multiplication looks like using rectangular form complex numbers. Not wildly difficult by any stretch of the imagination, but a little bit tedious. Now let's look at what happens if we use exponential form complex numbers. So let's say that A is instead the magnitude of A, e to the j theta A, and B is the magnitude of B, e to the j theta B. A being multiplied by B is just going to look like the magnitude of A, e to the j theta A, times the magnitude of B, excuse me, e to the j theta B. So I can multiply the magnitudes together. So I'll have the magnitude of A times the magnitude of B. What happens when I multiply two exponentials together?
Don't you get an exponential?
You do, but the arguments of the exponential add. So I'll have e to the j theta A plus theta B. So effectively, the angles add together. So multiplication using exponential form complex numbers is fairly straightforward. And then using polar form, A times B is just going to look like the magnitude of A times the magnitude of B with an angle of theta A plus theta B. Right. Lastly, let's look at division. So starting out with rectangular form, I'll have A is equal to A plus JB. And B will be equal to C plus JD. And then division is going to look like A divided by B. And actually, let me move the equal sign over because I'm going to have to do something to this in a moment. You'll see why. That's going to look like A plus JB over C plus JD. Okay. So the problem here is that if we look back at all my previous work here, whenever we were dealing with the rectangular forms, so in addition here, we have a well-defined real part and a well-defined imaginary part. Subtraction, well-defined real, well-defined imaginary. Multiplication, well-defined real, well-defined imaginary. But once we get down to division, we have a ratio of 2 rectangular numbers instead of a singular rectangular form complex number with a well-defined real part and a well-defined imaginary part. So we are going to fix this by multiplying by a fancy form of the number 1. And that fancy form of the number 1 is B conjugate over B conjugate. So I'm going to multiply that ratio by C minus JD over C minus JD. In my numerator, when I FOIL this out, I'm going to have A times C minus J A times D plus J B times C minus J squared B times D divided by C squared minus J CD plus J CD minus J squared D squared. So a couple of things here. Obviously, this cancels this. Negative J squared is just plus 1. So this is going to simplify to AC plus BD divided by C squared plus D squared plus J BC minus AD divided by C squared plus D squared. And now we have a well-defined real part and a well-defined imaginary part. So multiplying by the complex conjugate of the denominator here, or complex conjugate of the denominator over the complex conjugate of the denominator, effectively clears out any complex numbers from the denominator of the result, giving us only a real value. Another thing that we can notice really quickly here is that when I had B times B conjugate, the result was C squared plus B squared. This is nothing more than the magnitude of B squared, because the magnitude of B would have been the square root of C squared plus D squared. Okay. So that's another identity that we're going to wind up using later on. Anytime we multiply a number by its complex conjugate, the result is simply the square of the magnitude. All right. In polar form or exponential form, we have A is equal to the magnitude of A e to the j theta A, and B is equal to the magnitude of B e to the j theta b division is going to look like the magnitude of a e to the j theta a over the magnitude of b e to the j theta b, or the magnitude of a over the magnitude of b e to the, positive j theta a minus theta b. So we're taking the difference of the angles instead of adding them together. And this is equivalent to the magnitude of a over the magnitude of b with an angle of theta a minus theta b in polar form. All right, so that is all of the complex number stuff that I expect you guys to be able to do. I want to be very, very clear about this. I fully expect you to use your calculator to do 99.9% of your complex number manipulation in this class. That's going to make the in-class assignment a little odd, in as much as I'm not expecting you to show practically any work whatsoever because you're using your calculator to do it. So I'm just going to trust you that you actually used your calculators to come up with those answers. Whereas, if it were an in-person class, I could go around the room and answer questions and all that kind of good stuff and see that you're using your calculator correctly. Being able to use your calculator correctly for this stuff will literally make or break your exam score on this last exam. So if you need help, please, please, please let me know. You literally will not be able to make higher than probably a 15 on the next exam if you don't know how to do complex numbers with your calculator. So before we move along to looking at sinusoids, as a brief review, anybody have any questions, comments, or concerns for me?
Not right now. Thank you.
All right. So we are going to talk briefly here about sinusoids so that I don't talk for 2 hours straight next Monday. It'll just be an hour and a half. All right, so I am going to draw a generic sinusoidal signal here. I'm going to pre-apologize for my inability to draw one. So just for the sake of argument, let's call this a voltage waveform as a function of time. And here is my representation of a sinusoidal signal. Okay. So this signal, V of t, could be expressed in one of two ways. It can be expressed as a cosine function. So I'm going to have Vm cosine omega t plus some phase angle phi, or it could be a sinusoid or a sine function, Vm sine omega t plus some phase angle theta. So we're going to talk about the different parts of these representations, and for reasons that will become obvious, hopefully next class meeting, we are going to focus primarily on the cosine representation. Uses cosine as its basis. So let's first talk about this quantity Vm. So Vm is the amplitude or magnitude of the sinusoidal function and represents its maximum value. So the distance from the horizontal axis to the peak of the sinusoid is the amplitude of the sinusoid. And the distance from the horizontal axis to the negative most peak, this distance is also Vm. So that's our first thing. Now let's talk about omega. So omega is the angular frequency of the sinusoidal function. And it represents how quickly the signal oscillates. So unfortunately, it's impossible really to simply look at a sinusoidal signal and infer what the frequency is, okay? But there are things that we can look at that will tell us what that frequency is. So we're gonna have some sub things here. So the first of which is going to be the period of the sinusoid, okay? So the period could be measured in a couple of different places really that are easy. I'm going to choose to measure from this zero crossing to this zero crossing. So the period, and we'll write this down in a moment, is just the amount of time it takes for the sinusoid to repeat itself. The symbol for the period is capital T. So capital T is the period of the sinusoidal function and represents the amount of time it takes for one cycle to occur. F is the linear frequency of the sinusoidal function. And represents the number of cycles per second. So F is simply the inverse of the period, okay? So if the period is the amount of time it takes for one cycle to occur, the linear frequency is the number of cycles that occur in 1 second. So they are inversely related to each other, okay? Coming back to omega, omega is simply 2 pi times F. So 2 pi is the total angle traveled in one cycle. So the angular frequency is the angle covered multiplied by the frequency, which means that it can also be expressed as 2 pi over the period. So if we can measure the period of our sinusoidal signal, then we can determine its angular frequency. One thing that I want to point out here, the angular frequency omega is always measured in radians per second. So even if I don't explicitly tell you what the units are, it is always measured in radians per second. All right, so the last thing that we have to deal with is our phase angle, phi. So phi is the phase angle of the sinusoidal function. And it represents how much the signal is shifted in time. So let me scroll up here so I can kind of explain what I mean by that. So if we are looking at this red waveform as a cosine function, it is shifted in time slightly to the right. And I can say that because I know that for a cosine function with a phase angle of 0, it should hit its peak value at t is equal to 0. But instead, it hits its peak value for some positive value of t, right? So it is shifted slightly to the right. Another way to think about it is that it is delayed because it is hitting its peak value at a point in time later than t is equal to 0. If we looked at this signal as a sine function, we know that sine at t is equal to 0 should be 0. So this would be an example of an advanced function. So it's time shifted to the left, because it is hitting 0 and increasing at a negative value of t instead of hitting 0 and increasing at t is equal to 0. Okay. So our phase angle is just a representation of how forward in time or backwards in time our waveform has been shifted. Okay. So positive values for phi indicate that the signal has been shifted to the left. You may also hear this as advanced by delta t is equal to sorry, I have to look at the units here. I don't remember this off the top of my head. Radians per second. Radians. Yeah, delta over omega, so that should give me angle over angle per second is going to give me seconds. Yeah. So positive values for phi indicate that the signal has been shifted to the left by some amount of time that is given by the phase angle divided by omega. Negative values of phi indicate that the signal has been shifted to the right. Or delayed. By some amount of time, that is phi over omega. Now, this left shifting for advancing and right shifting for delaying may seem counterintuitive. It all comes about by the way that we read a graph, okay? So on the left-hand side of the graph, where t is negative, that indicates earlier points in time than t is equal to 0. And on the right-hand side, where t is positive, that means later points in time where t is equal to 0. So it seems counterintuitive, but it does make sense if we understand how we experience time on a linear scale. Okay. All right, so before we move along to trig identities, I actually want to take a look at one of the more difficult homework problems that you guys are asked to do. So give me just a moment to pull up the web work. Sorry, I'm looking. I know it's going to be homework set number 19. I am confused as to why homework set number 20 is open and is due tomorrow. I'll need to fix that because it should be due later than homework set number 19. So this is the problem, homework 19, problem 3, that really gives you guys a lot of problems. We are only going to look at part A here, and we're not even going to look at all of part A. Parts B and C will be handled by trig identities and complex math that we're going to learn on Monday's class meeting. Okay. But we're just given a small amount of information regarding a signal, and we are expected to be able to effectively reconstruct that signal mathematically just based on this small amount of information. And I believe that we're fully capable of doing this based on the 10-ish minutes of review that we've done to this point. Okay. So we are told that a sine wave f of t is 0 and increasing at t is equal to 10.8 milliseconds. So I'm going to draw that. So here is my graph. And this point in time will arbitrarily be 10.8 milliseconds. And we know that our function is 0 and increasing at this point. Okay. The succeeding positive maximum of 9.6 occurs at t is equal to 22.1 milliseconds. So I'm going to put the maximum value here. .6, and it occurs at a time of 22.1 milliseconds. Double check the numbers here. Yep. And I'm just going to connect the dots to make it look sinusoidal. So this is the information that we've been provided with. And we need to express the wave function in the different forms. Okay, that's the only information that we were provided. This seems like not a whole heck of a lot of information, but it is actually quite a lot. So let me explain what I mean. So if we go from 0 and increasing to a positive maximum, this amount of time is 1/4 of the period of our function, because we've gone through 1/4 of a cycle, right? Another 1/4 would bring us back down to 0, and then we'd hit the negative peak, and then we'd go up to the positive peak, and then it would repeat over and over again. So since we know the amount of time that it took for 1/4 of the wave to go, we can then extrapolate what the period is, and then we know that omega is 2 pi divided by t. So we have enough information to figure out what omega is. Well, the magnitude of this guy is just 9.6, because we were told what the peak value was, and the magnitude of a sinusoid is literally just its peak value. So the only thing that we have left to figure out is our phase angle, right? So lowercase t. This amount of time, 8 milliseconds, is by how much this sine function has been delayed. So our angle theta, I'm just calling it theta because we're using a sine function, is going to be negative delta t multiplied by omega, where the negative sign is because we have a delay to the right, or a time shift to the right. Now, one other thing that I want to look at here really quickly, we're told that we want our phase angle to be positive, but as small as possible and in degrees. So to convert it into degrees, we would multiply by a factor of 180 degrees over pi. So that's going to convert our angle that was in radians, because radians per second times time is an angle in radians, times 180 degrees over pi radians gives us an angle in degrees. And then because we want it to be positive, we're going to add 360 degrees, which will force that negative number to be a positive number. And it will be the smallest possible positive number because we're only adding one cycle. Okay. So that's the hard part of homework 19, part 3. Parts B and C are literally just trig identities that we're going to learn here in the next few minutes. All right. So let's go ahead and hit you with trig identities. Just a moment, please. All right. So the first trig identity that I'm going to give to you guys is that cosine of omega t plus some phase angle phi is going to be equal to the sine of omega t plus that same phase angle plus 90 degrees. So all this means is that if we want to convert a cosine function to a sine function, we simply add 90 degrees to the phase angle. Trig identity number 2 is the opposite relationship. So if we have sine omega t plus some phase angle theta, that will be cosine omega t plus theta minus 90 degrees. Or in other words, to convert from sine to cosine, we subtract 90 degrees from the phase angle. Okay. Our third identity, if we have a negative cosine function, and we want to make it a positive cosine function, we simply add or subtract 180 degrees. It does not matter whether we add or subtract. We're simply moving a half cycle ahead or a half cycle back. And the result is exactly the same either way. Have effectively the same relationship for changing negative sign functions into positive sign functions. Negative sine omega t plus positive sine omega t plus theta plus or minus 180 degrees. So these are the trig identities we're going to use when we are comparing sinusoids. And we'll talk about that here in a moment. I want to get to the other trig identities that we're going to use in this class as well. Okay. So trig identity number 5. Let's say that we have sine of alpha plus beta. Okay. So this is the sine of the sum of two angles. Can be expressed as the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. If instead we have cosine alpha plus beta, that's going to be cosine alpha, cosine beta, minus, and this minus sign is correct, sine alpha, sine beta. And now we're going to have two similar ones for when we have the difference of angles instead of the addition of angles. So sine of alpha minus beta is going to be minus cosine alpha sine beta. And cosine alpha minus beta is going to be cosine alpha cosine beta plus sine alpha sine beta. Okay. These are going to be utilized when we look at circuits in the time domain, which will be very brief. And the reason why our analysis of circuits in the time domain is going to be very brief is because it's going to force us to spend 25 minutes playing around with trig identities as opposed to actually doing any real circuit analysis whatsoever. So we're going to develop a better way, but these are the ones that are going to be used. Okay. We have a couple of other trig identities that we're going to use later on in this class. Number 9. Oh gosh. So cosine of, let's just call it cosine alpha cosine beta. So if I multiply two cosine functions together, this is going to be 1/2 cosine alpha plus beta plus 1/2 cosine alpha minus beta. We could technically develop relationships for cosine alpha times sine beta and all that kind of good stuff. But because we can convert every sine function into a cosine function, I'm not going to bother. This is the one that we're going to wind up using the most. And then lastly, we have a very special one called Euler's identity. And it relates sinusoidal functions to complex numbers. So Euler's function says that e to the j omega t plus some phase angle phi is equal to cosine omega t plus phi plus j sine omega t plus phi. This is literally nothing more than the relationship between exponential form complex numbers and rectangular form complex numbers that we developed at the very beginning of this class, just in a more formal statement. Okay. So these are the 10 different trig identities that I'm going to expect us to be able to use. That being said, this one and this one are the only ones that we are not going to be able to come up with a workaround for. So if you have to remember exactly 2 of them, it's the 2 that I've put a star by. All the others will figure out a way to not have to memorize them. All right. You know what? I think that's a good stopping point for today because I've talked for 80 minutes straight. So, yeah, so we'll kick things off with comparing sinusoids at the beginning of our lecture on Monday, and then we'll go on to time domain analysis and see what shakes out.
All right, Dr. Hartman, I've got 2 questions before we go today.
Yes, sir.
So the first one is about the ICAs upcoming. I don't think there's any due dates posted for them yet. I didn't know if you knew or not or had planned on doing it in the future.
Did not do that, so I will put that on my list of stuff to do.
All right, sounds good.
Right now, yes.
And then second question, I've had this one since the first exam, but I noticed the exams are 105 points. Are they scaled out of 100 and that 5 points is like kind of like a bonus extension or how does that work?
You're exactly right. So they are
Okay.
out of 100 points and the 5 points extra is a bonus. So there is a
Okay,
small
awesome.
bonus built into every test.
All right, sounds good. Yeah, I kind of figured so. I just wasn't 100% sure, so I just wanted to clear that up.
Yep, you're not the first person to have asked me about that today, actually. But yeah, so if you scored over 100, that makes your life easier.
All right, yeah,
Later
sounds
exam.
good. I wish I did, but that would be amazing, but I did.
Anything else I can help you with?
No, sir, that'll be it for today. I appreciate your time.
No problem. Thank you
All right, have a great
for listening to me rant about numbers for the last 80 minutes.
Yes, sir. Have a great day.
You too. Bye.